All right, today we're going to talk about probability density functions and cumulative distribution functions, with the key term being density and distribution. Now, in previous lectures, you've heard of, in discrete random variables, you've heard of the probability mass function, and that's where values can take on a very certain discrete number. And we're going to talk a little bit about, there's some important differences between going from discrete to continuous in that sense. But in order to motivate that, I just want to do a quick review here. So with the discrete, we're going to use this side here for discrete, and we're going to use this for continuous, right? Just so you see the difference. So let's start with the idea of a probability mass function, right? So a PMF, or P of x, right? So if you recall, right, you have certain values that x can take on, right, here, and so that becomes your probability mass function. So there's set values here that x can be, and if I wanted to take the probability, let's say that that A was less than or equal to S is less than or equal to B, right? And if I've got A and B here, then I'm basically just going to sum, right, across these values, A and B, and I'm going to, sum the frequency, right, the mass function, right? So there's some sort of P of x along this axis right here that's, whatever value, something greater than 0. And so I can just say, what's the probability of getting A? What's the probability of getting B? I add them together. That gets me the probability of getting between A and B, right? Or if there was 3 blocks, then you would add that third block in there, right? So that's how we understood calculating a probability with the probability mass function, if you recall, right? And then we added this idea of a cumulative distribution function. So this is the CDF. And if you recall, the equation for the CDF, we use capital F of x, right? So this axis here is capital F of x. It's a number that goes from 0 to 1, right? And it's the cumulative probability that something's happened, right? So it's F of x. And if we were to say, define this, it's the probability that our random variable, right, capital X here for a random variable mapping rule, is going to be less than or equal to some number x. This is the x that actually goes here, right? Some number there. That's going to equal to the sum over the values of y such that y is less than or equal to x. And it's going to be the probability of y, where this p, right, is referring to that PMF, right? So don't get tricked out by the fact that I have a different letter here. I'm just trying to keep a difference between this letter and this letter, right? So this is essentially, this is saying, y is saying all the values from x and lower, right? From negative infinity all the way up to this value, right? This x is the upper limit of the sum. That's what goes into the f of x, right? So that's a slight difference. But when we're constructing this, what we're going to do is we're basically going to say, hey, there's a little bit of value here. It doesn't go down. A little bit of value. Then we get a little bit bigger. Then we get a lot bigger, a lot bigger, a little bit bigger, a little bit bigger, right? And so the idea is where there's big chunks are, you're seeing bigger step sizes up, right? So it accelerates a little steeper and it smooths out. So what is, if this is the distribution, right, then what the CDF is saying is, what is the probability that x is this value or less? Well, if the distribution has an upper limit here, right, remember the PMF, all these values sum to 1 in a proper PMF, right, over the support. Those are the range of values that x can be. So if we're saying x can go from here to here, right, what's the probability that your x is less than or equal to, whatever this is? Let's call it z, right? What's the probability? Well, the probability that something happened is 1, right? All of these things add up to 1. That would equal 1. Right? What's the probability that we're less than this value over here? Let's call it z star. Well, the probability you're less than z star is 0 because there's no mass there. All the probabilities are occurring here, right? And you're just adding those probabilities. And this, if you recall, with the CDF, if you were wanting to say, what's the probability that I'm less than z? Well, if I look at z here, I should be able to read that up to the value here, over to the value 1, and say, hey, I get the same probability. What's the probability that I'm less than b? Well, if I find b here, right, I should be able to read that up to the value here, read it over, and then, you know, I get my probability or whatever the value is right there. That's how I'm reading the CDF, okay? That's a review. I hope that makes, that's a good reminder. When we're talking about the density function, right, and we're in the continuous case, it looks very similar. What we're going to do is we're replacing the PMF with the PDF. We are replacing P of x with the little letter f of x, right? And this is a continuous function. And so now the function is going to go something like this, right? It's not going to have these bins anymore. And so with the smooth function, if I want to say, hey, I'm going from A to B, right? Instead of having this equation where I'm going to say, hey, what's the probability of A, and I'm adding this mass with this mass, what I'm going to do, instead of adding those, I'm going to be, so I'll say A less than or equal to X less than or equal to B. I'm now going to be saying, here is my integral instead of a summation. I'm going to go over the interval A to B, and I'm going to multiply, I'm going to have f of x, that's the distribution function, that's this frequency, dx, okay? That is now going to be how I'm going to change that, that function, and it's basically going to be taking the area under the curve in this interval. That is the PDF. Okay. Now the CDF, right, in the same way, is going to be, we don't do these stair steps anymore, right? So how are we accumulating the value? Well, I'm still going to use capital F of x, right, for this value. It's still going to range from 1 to 0 because keep in mind, like a PMF, the whole thing had to sum to 1. In a PDF, right, the whole thing has to sum to 1. What does that mean? That means that the integral from negative infinity to infinity of f of x dx equals 1, right? That's a rule. If that doesn't occur, it's not a PDF, okay? So the probability something happens is 1, right? So that's what that is saying, right? So probability from negative infinity to infinity is 1. So what we're doing with the f of x, just like we were saying, hey, what's the probability a random value is less than some function, and that's the function here, right? What we're saying is f of x is equal to the integral from negative infinity to x. That's the value that goes there. And what we're going to do is we're going to say f of y dy, just like we did here, right? And this you know, is only to tell you that it's a different letter than this, right? So the function in the CDF, right, what you're actually plotting is the upper limit of integration, right? The thing that you're plotting down here on this x is the upper limit of integration. Different than the x here, which we've just substituted with y. So now what happens here? Well, just like when we were building it over here, I'm going to start, and it's like little slices, right? So it's going to be a little bit of growth. And then when we get to these higher points, right, we're going to have the maximum slope of growth, and then it's going to filter out again, right? And so that is what and then it's just going to continue, right? So this is what my CDF looks like. And so when I ask f of x, right, what I'm saying is, what is the area from negative infinity up to that value, how much probability has accumulated, right, is what we're doing. And so you can see that there is an analogy from the discrete to the continuous, from the discrete to the continuous, right? You'll notice that when the density function is at its highest, the slope is at its highest here, where you're accumulating the most, right? Which means a couple of things, right? It means that I can also get this, right? F of x is the derivative with respect to x of f of x, right? Or you could say f prime of x, right, is the density function. So there is this interesting relationship which we call the fundamental theorem of calculus, right? Which is that the distribution function, right, the derivative of the distribution function is the density function. The density function, right, if you integrate the density function, you get the distribution function, right? So there's this relationship with him that's fundamental to calculus. Now, what that means is the density function is really telling you a rate of change at which you're accumulating probability over time, right? It's this rate of change in that. It also means, right, that if I were to say, what is the probability, right? What is the probability that x, sorry, I said f of x, but I need to say, what is the probability that x equals a specific value in a continuous thing, right? Well, think back to calculus a little bit. What's the likelihood you hit A? Not A 0.001 or 0.0001 minus, like off of A. You just miss it a little bit. There's an infinite amount of points surrounding that exact value of A. So the probability that you equal a certain value is 0. Well, what does that mean? That means that when we're looking at this, right, this is synonymous as saying, right, the distinction between less than and equal does not matter, okay? The other thing that we're doing with this is we're always dealing with less than probabilities, right? So f of x is saying the probability that x is less than, right, a given value. This is the random variable less than x, right? It's always saying, what's the probability you're less than a specific value, not more than. So how do we ask the question of what's the probability you're greater than b, right? If I want to say, what's the probability x is greater than b? Well, I either now need to say, given that everything adds up to 1, I can say 1 minus f of b, right? 1 minus what I don't need anymore, okay? Or 1 minus the integral from negative infinity to b f of x, right? Or if I have the distribution, the density function, I just want to work with that, I can also say b to infinity f of x dx, okay? Now these can kind of, this is a lot of information. This requires some meditation. This is probably one of those lectures you're going to want to replay a few times, especially as we go into some examples.